Going to get this set up to record. And I'm gonna mute everybody. So again, just to remind everybody to unmute to ask questions, and absolutely please feel free to interrupt, interject, whatever. Just because we're on Zoom doesn't necessarily mean this isn't a roundtable kind of thing. So all right, everybody, I'm going to go ahead and get started. It's I got 32 past the hour here. So um, here's the agenda. You can see I won't go into any detail on that. Just deal with that as we go here. So all right. So first thing is, and we have Guy Babbitt on from C0 to talk about this. So we've got the particulars up here, and if you'd like to register, please use that link that I provided at the bottom. But Guy, if you want to give us a little sales pitch for this, that'd be great.
Yeah, sure. Some of you were with us. We did one of these, I think, in November, and really had a good enough time. Some great conversations with people. We just decided why not do it again. So the schedule didn't line up for us to. We either had to push it out almost to April or do it next week. So a week from tomorrow, Thursday, from 4:30 to 7 at our place, we're going to just sort of open the doors up, allow people to. We'll show people the shop if they want, but we'll just have drinks and some light apps and really just trying to get everyone together again. So it would be helpful though if you want to attend, even if you're uncertain, maybe just a sign up would help us give us some idea, so we plan accordingly.
Okay, thanks, Guy. And just so, Guy, you're not confused, I created this proxy at
I
Tiny
saw that.
URL
Yeah, great.
just
Thanks.
just to make that a little bit easier, and that does link to your registration page. And I will put in a plug. Boy, last time the food you had was amazing. Are you doing the kind of a similar spread again?
Yeah, I mean that's sort of the plan. Just kind of repeat what we did. It seemed to work pretty well. So yeah.
Yeah, it was a great opportunity to network, and so I guess probably enough said, but you can always contact me or contact Guy, if you have any questions about it. So, all right, then that's the first event coming up. The next one is there's going to be three of these public meetings for this three-station fueling grant that was awarded to CSU and New Day Hydrogen. You can see the Energy Institute here, the CSU Energy Institute's logo. And they're going to be holding three of these meetings. The one is going on actually right now in um, down in Pueblo. I tried to convince them not to hold it during our meeting, but it just had to happen. But the next one is going to be also another event up in Fort Collins, and it'll be at the Powerhouse. If you've never been in there, that would be an excuse maybe to come to this to see that. But the purpose of the meeting is just to talk about the grant, to talk about the project, what's going on. There'll be some folks from some of the fleets there that we're trying to enlist to be the customers, of course, for the fuel. Everybody's welcome. They do ask that you RSVP to Buford. And by the way, I had a fat finger typo in the newsletter. I had Buford's email incorrect. So I assume people probably figured that out, but I had I had a bandage on my hand. And I had fatter fingers than usual. So anyway, just be aware that that was incorrect in the newsletter. All right. There will be another event. Like I say, Pueblo is going on right now. The Fort Collins one is on the 27th, and then a Denver event is being planned, but we don't have a date or a location for that yet. So if you do want to attend one of these three and you want to wait, if you're in Denver and you want to wait for the Denver event, you can do that. And I'll certainly post that once that comes up. All right. I wanted to point out to folks that I'm a big fan of the Weather Channel, and I imagine plenty of you have seen that. But it's interesting, the Weather Channel is doing a lot of climate change coverage, and it's quite good. And this is just one example, but I used my phone and I just took a picture of the screen the other day. They were talking about is the global temperature increase actually 0.9 degrees C higher than what the IPCC thinks it is. And I think the reason for that is if you look at, let's see, let me get my laser pointer here. Um, the IPCC, I think, is using this point in time as a baseline. And there's been some scientists that have gone out and done data on sea sponges, believe it or not, which is this blue data. And they say, hey, you know what? Temperatures are really quite a bit lower, maybe than we think they were, or what is being used for as baseline. Now, the criticism of this is this was only in an area near Puerto Rico. And so the scientists are planning to go out and do some things in the Pacific and Atlantic and other things as well, just to look at this data. But anyway, the point of all this is that if you're not a watcher of the Weather Channel, you might start tuning that in because there's some pretty interesting climate change information that they're covering there. All right. So, Jeff Ellis has been patiently waiting. And Jeff, go ahead and unmute yourself. But you can read this faster than I can say it. Jeff is a research geologist at the US Geological Survey, and he's also on the faculty at the School of Mines. And Jeff and I just did a podcast. I think it aired last Friday, so you may want to listen to that. But I asked Jeff to come on the meeting and just talk to us a little bit about geological hydrogen. Those of you that haven't been hearing what's going on, there's quite a bit of interest, quite a few companies, and a lot of it in Colorado. So, Jeff, I'm going to stop sharing and let you share, and you've got the floor for as long as you'd like.
Okay, great. Thanks, Brian. Let's see. Are you seeing my screen now?
Yeah, we got it.
Okay, great. Yeah, I thought what I do, I mean, well, again, thanks for the invite. Happy to be here to talk with you all this afternoon. And you're absolutely correct that there is a really growing interest in this subject, really in the last year or so. And in fact, if you didn't see it in Science Magazine, at the end of every year puts out their list of the top scientific breakthroughs of the previous year, and they listed geologic hydrogen as one of their top 10 breakthroughs of the year. And actually they had the American Association for the Advancement of Science had their annual meeting here in Denver just last week. And I, along with my colleagues from the School of Mines and from CU Boulder, were invited to a session dedicated to geologic hydrogen. And so this is just some slides that I have from that presentation that I thought I would share with you today. And I thought I would just start, I'm sure this is very familiar to everyone on the call here, but just give you a little context about hydrogen as an energy supply and where we are today and where we think we're going with this. And this is from a IEA projection from a couple of years ago now, where I think now for 2022 globally we produced about 100 million metric tons or megatons of hydrogen, and most of that, almost all of it, in fact, comes from fossil fuels, from mostly natural gas, but also some from coal. And in the process of making 1 kilogram of hydrogen, we release about 10 kilograms of CO2 to the atmosphere. And in their projection, and I've seen similar things from other organizations, IEA thinks that we're going to need about somewhere over 500 megatons of hydrogen per year to meet demand for certain sectors that are hard to decarbonize. So things like aviation in particular, or other heavy industrial processes and so forth. And of course, to do this and meet net zero goals, then we have to replace this hydrogen from fossil fuels with clean sources of hydrogen, low carbon. And so they envision that this will come from a mixture of so-called blue hydrogen, which is hydrogen from fossil fuels, carbon coupled with carbon capture, or also green hydrogen from electrolysis of water. But there's increasingly, I think there's concern about how we're going to get there in terms of making all this hydrogen. There's a lot of minerals that will be needed, as well as just the expense of doing all this carbon capture and so forth, it's going to be challenging, I think. And importantly, in these discussions, hydrogen is viewed exclusively as a medium for energy storage and transport. And so you have to put energy in to get the hydrogen before you can get it back out. But what is lacking is any discussion about the potential for natural hydrogen to actually be a primary energy resource. And so that's what we're going to talk about in the next few minutes here. So in fact, hydrogen is really quite ubiquitous on Earth. It's a lot of people don't realize this, but the air that we're breathing now has about a 0.5 part per million concentration of hydrogen in it. The world's oceans are super saturated with respect to hydrogen. We very frequently find hydrogen in soil gases. I was just in in North Carolina last week, looking at soil gases, looking for hydrogen, and we found very high concentrations. In fact, in one location, we found over 1% hydrogen leaking out of the ground and out of the soil. And it's not only at the surface, it's also in deep boreholes and mines underground. It's frequently found. This map here shows observations documented in the literature of hydrogen concentrations in excess of 10%. But if we look at hydrogen, median concentrations of hydrogen observed by different geologic settings, which as is shown in this histogram here. What's really of note is that if we look at petroleum fluids, we find that it's very, very low. And it's, in fact, it's quite rare to find more than trace level concentrations of hydrogen associated with natural gases in petroleum systems. And so for this reason, geoscientists have concluded that probably because hydrogen is a small molecule, it's very light and diffusive, and it's also very reactive. Microorganisms and inorganic reactions consume hydrogen readily. And so for these reasons, we probably can't form accumulations. And that even though it's quite ubiquitous, we just can't get economic accumulations like we do with oil and natural gas. This has been the paradigm for many decades now. But there are some really good reasons to question that thinking. The first being that petroleum exploration is not actually targeting hydrogen. And in fact, the oil and gas industry spends billions of dollars every year, has very sophisticated technologies, and they still routinely drill dry holes. They don't find petroleum very often in many places where they think they should. And so I think it might be a bit naive to think that we should just find hydrogen without actually even trying to look for it. Additionally, the geologic settings where we know that hydrogen is being generated and it might most likely would be found in accumulations, these are really not the places where we're looking for oil and gas. And so oil and gas exploration is typically restricted to sedimentary basins where we have these organic rich rocks that are the sources for oil and gas. But hydrogen is generated in hard rock settings, more volcanic, more magmatic, or hydrothermal settings. So these are really not the places where oil and gas companies are exploring. And it's possible that you can have hydrogen in some of these sedimentary basins where we're looking for oil and gas. But it's important to realize that the process of generating petroleum from a petroleum source rock is actually a hydrogen limited process. And so, in fact, when we measure the quality of a petroleum source rock, we measure the organic hydrogen content, something we call the hydrogen index, that tells us how much petroleum we can expect to get out of that source rock. But what this means is that if you have an external source of hydrogen, so in this cartoon, for example, we see some deep faults where hydrogen is leaking out of the interior of the Earth. If that were to migrate up and encounter petroleum source rock, that hydrogen most likely would get incorporated into hydrocarbons. And so we would see methane and not actually hydrogen. So we really should not expect to find any hydrogen associated with hydrocarbons. Now, mining companies do routinely explore for minerals, precious minerals in these hard rock settings. But in their exploration activities, they very rarely look at gas composition. If they measure gases at all, they are interested in gases from a safety perspective. And so they measure the explosivity of the gas, but that doesn't actually tell them if it's hydrogen or hydrocarbons or something else. So they really don't know what's there. And so the takeaway here really is that we just simply haven't been looking for hydrogen in the right places with the right tools. And so in this context, about 12 years ago now, there was actually an accidental discovery of an accumulation of natural hydrogen in the country of Mali in West Africa. They were drilling for water, and they accidentally encountered some flammable gas. And they later went back, an oil and gas company later came back to that site and drilled a well to produce the gas, expecting it to be methane. When they measured the concentration, they discovered it was almost pure hydrogen gas. And so as news of that discovery has gotten out, there's been a growing interest in natural hydrogen as a primary energy resource. And we've had exploration activities ongoing now in Europe and other parts of Africa, and in South America and Asia, and here in the US. And in fact, the first well that was drilled explicitly targeting natural hydrogen was drilled not far from here in Nebraska back in 2018. And subsequently, we've had additional wells drilled on what we call the Mid-Continent Rift, which runs roughly from Kansas up through Iowa and into Minnesota. And there are several more wells that are planned to be drilled later this year in that region. And then also there were a couple of wells drilled late last year in South Australia at a site where 100 years ago, an oil and gas company had been looking for oil, and they accidentally found about 70% hydrogen in some rocks deep underground. And they walked away from that because they were looking for oil. And so an Australian company now became aware of this old discovery and went back and re-drilled those areas. And they found almost the exact same concentration of hydrogen, suggesting that this is actually an accumulation, not just some transient passing amount of hydrogen. And in fact, there's also a project that's in the planning stages in the country of Oman to try and actually stimulate natural hydrogen generation. And I'll talk a little bit more about that in a second. So one of the questions that I really pondered early on, and I'm frequently asked by other people, is how much hydrogen could really be in the subsurface? Could this really be a resource? And so to try and get at this, I did some work with a colleague of mine. This is a study that we did that's currently in review at the journal. So this is our still preliminary results that haven't been published yet. But we built a simple model shown in this cartoon where we have generation of hydrogen and have it leaking up towards the surface, and some of it getting into traps and getting consumed by reaction and then escaping to the atmosphere. And then we put a range of values on these various inputs based on what we know about hydrogen, as well as using analogs from other fluids like petroleum and helium and so forth. And then we were able to run a Monte Carlo simulation of all these various inputs. And then we can assume that today this natural system has been sitting here for millions of years, and so it's at steady state. And so we can calculate how much hydrogen might be trapped in these reservoirs. And so when we do that, we get this this distribution of output values here shown on this histogram. And the range of values is really quite large, anywhere from perhaps thousands of megatons up to maybe billions of megatons, with the most probable value on the order of about 5 million megatons of hydrogen around in the entire Earth's crust. And this is really an important point because this is a global model for the entire Earth's crust. Most of that hydrogen is very likely going to be inaccessible. And by that, I mean that it's simply going to be too deep or too far offshore, or in accumulations that are much too small that never would be economic to produce. But if we think for a minute, if there really is 5 million megatons of hydrogen trapped in the subsurface, if we could just find and produce 2% of that, that would represent 100,000 megatons, which could actually supply all of that 500 megatons per year that we talked about a minute ago for 200 years. And so the point of this, the real takeaway, I think, is that it's most likely that there is a large amount of hydrogen in the subsurface. And the question really is it in accumulations that we can actually find and produce economically? And so we need to understand the geologic processes that can lead to these accumulations. And so to do that, we are working now in the USGS on developing what we're calling the hydrogen system. And this is a geologic model that we can use to explain and predict where we would expect to find hydrogen accumulations in the subsurface. And we're starting with with the well-known a system called the petroleum system, which comprises elements of source, migration pathways, reservoirs, traps, and seals, and so forth. But we're starting with that, and we're modifying it for hydrogen. The source rocks are going to be different. The reservoirs and seals may be somewhat different, and so forth. But we can use this general framework to try and understand how hydrogen might accumulate in the subsurface. And another key consideration is how we might actually exploit hydrogen resources from the Earth. And so there are now ideas about three conceptual types of what we might call plays in the petroleum world. And the first being what I call natural accumulations. And so these are directly analogous to conventional oil and gas type of accumulations, where you have an external source, for example, potentially radiolysis of water generating hydrogen, or reduction of iron, oxidation of iron-rich minerals and reducing water to generate hydrogen. And then that hydrogen migrating up through the subsurface and encountering some porous rocks where an accumulation can form beneath an effective seal. But it's been suggested that because the rate of hydrogen generation can be so fast, we could actually observe this reduction of water in real time in places like mid-ocean ridges. And so people have suggested that perhaps we don't even need a reservoir and a seal, but that we could actually just produce hydrogen as it's being generated in real time, something that I call natural generation. And a third potential is this idea that we could actually stimulate the generation. As I mentioned earlier, there's actually a project now being proposed to work in Oman to try and stimulate some iron-rich rocks. You could imagine that if you had these rocks buried at depth where they were at the appropriate temperature range, but they simply didn't have water moving in contact with them to be reduced, you could drill down into them and fracture them or stimulate them somehow to generate surface area, and then inject water and start producing hydrogen in the subsurface. But I think it's important to recognize that the viability of these ideas, the generation and the stimulated production, these are really unknown. These are very, very much research topics. However, these natural accumulations, this is, as I said, analogous to petroleum. We also know that there are helium accumulations and CO2 accumulations that very much follow this model. And we have this known accumulation in Mali, in West Africa, that actually contains pure hydrogen. So this is a proven concept. But it's also important to recognize that global model that I showed you earlier, that is only for these natural accumulations. And so if there are additional resources that could be accessed through this natural generation or stimulated generation, then that could significantly add to what the resource potential is. So certainly is worth doing research into trying to understand those better. So in the USGS now, we are now taking this hydrogen system model that we have, and we are now trying to apply it to understand where are the best places to look for natural hydrogen resources in the US. And so we're developing a map of prospectivity. And this is our model here. We don't have time to go into it in detail, but we can discuss it during the Q&A if you're interested. But we're essentially combining all of these components together to calculate a net prospectivity at every location across the US. And our plan then is to actually publish a web-based interactive map, because there's so much uncertainty about how these hydrogen systems might work yet, where this is still very much in the nascent stage, and there's a lot of research going into it. And so if we were to publish a static map, I think it would be outdated in 6 months or a year. And so we're going to put out a dynamic map where users can actually decide what components they think are important, what they want to look at. And so, for example, if you didn't think that deep sources were a viable source for natural hydrogen, you could click on that and turn that off, and the map would update. Or if you want to see how much weighting we've added, or how important, what are some of the settings on this serpentinization type iron reduction reaction, you could click on that settings, and you could see how these are being affected. And if you thought, well, this isn't maybe it's not as important as the USGS thinks, you could turn that down, and the map would then update in real time. And then you could go back to the main map, and it will show you again what the prospectivity is. And then as we get new data and new understandings, we'll be constantly updating this map. And so this is something that we're working on, and we hope to get out publicly in the coming months. And lastly, I'll just point out that in addition to our work within the USGS, I'm also working with colleagues at the Colorado School of Mines and the University of Colorado in Boulder on a joint industry consortium. We now have 8 companies that are working with us. It's a mix of hydrogen startup companies as well as major oil and gas and mining companies. And we're conducting research in a wide variety of areas that impact this, ranging from understanding these hydrogen systems to developing surface and subsurface exploration tools, and as well as integrating all of this with reactive transport modeling. And then we were also one of the awardees of some funding recently announced by the Department of Energy to conduct research into this idea of stimulated hydrogen generation. And so we will be adding that to our research program in the coming months as well. So just to give you a summary of some of the big takeaways, I think it's very likely that there are large quantities of natural hydrogen in the subsurface, and we just simply haven't really been looking for it. We didn't know where to look or how to really look for it. And so now we're beginning to develop the tools and ideas to try and figure out where are the best places to look and what are the strategies and tools that we need to actually do that. And so the work is just beginning, but it's really exciting that there's a lot of potential here. And finally, I'll just point out that if you haven't seen this article that was published in Science about a year ago, they've done a very nice job of summarizing much of what I've said here and actually going on into greater detail. That I would recommend you take a look at that if you like more information. So thanks very much. I'm happy to stick around and chat about any of this if you'd like.
Yeah, thank you, Jeff. Speaking of that article, I had previously created a shortcut to that, and I put that in the chat. It's a tiny URL. So that's a little bit easier to type out than that. And that's a great article
Yeah.
because it's got some good graphics in, and you showed one of them. I saw that. So thanks. So we're going to open this up to questions. And I know just to kind of give everybody a chance to get ready to unmute yourself and ask your question, Keith Whipke asked about the well in Nebraska. That's Natural Hydrogen Energy LLC. That's Vyacheslav Zagonic's well, and I visited that, and it's my understanding it's producing. Do you know much about that, Jeff? I know Slava's been kind of close to the vest with information on that.
Yeah. To my knowledge, it's not been producing. They've done some flow testing on it, and I did see some results that show that they have confirmed absolutely that there is hydrogen in the well, but we don't know what kind of production volumes they might get. And again, my understanding is that the holdup has been that they are looking for investors to finance the operations to get the testing done. So.
Yeah, I know they had some investors to drill. As a matter of fact, the day I was out at that well site, one of the investors happened to be there. I didn't talk to him. I just said hello. But yeah, I wish him luck. But I know that this is getting pretty competitive. So I think, like I say, he's holding things a little bit close to the vest and being a little bit careful. Now, Jeff, before I forget about this, USGS is going to be putting up the website. You just showed us some things. Any idea when that's going to happen?
Well, unfortunately, we're behind my sky. I had hoped that we'd have our map ready by now, but we're behind schedule. So we're still a few months away, I think. Probably it'll be later this spring by the time we get that up. Yeah.
All right. Well, certainly once that's up, if you let me know, I'll announce it on this meeting as well as put it in the CHN newsletter.
Yeah, absolutely.
Yeah. All right. So I'm hogging the platform here long enough. Let's see. We got Frank's iPhone is on it. And is that Frank Zamataro? And Frank, you're going to have to hit *6 to unmute yourself.
Okay. Hold on.
Yeah, we got you. We got you.
Oh, okay, good. Hi, everyone. Hey, great presentation. Very exciting stuff. Mining as a general industry is dirty. And obviously, I'm interested in understanding because we're applying our technology to wastewater from mining to collect excess flow and pressure to make clean electricity. I'm curious as to the process of, is there a lot of water used in mining hydrogen? Just a little more understanding about the process and potentially how is it dirtier than oil, cleaner than oil? I'm just trying to put it into some context.
Yeah, sure. So the well, as I mentioned, there's sort of these three concepts of the conventional accumulations and then the natural generation or the stimulated. And in terms of the natural generation, well, the stimulated is very much a research topic, and I think there are a lot of engineering challenges and environmental concerns that have to be addressed. And DOE is well aware of this. Their research program has funded a lot of effort into mitigating those, being aware of what they are and so forth. So that one, I think I would set that aside, but we can talk more about these producing from a conventional accumulation or even from a flow. I think we do have good analogs, and I would say that the conventional accumulations are very much like producing from a conventional natural gas well, or even helium, or a helium well. And so there is minimal water, contamination, and the footprint also is very minimal, and so there really I think is a relatively minimal environmental impacts of producing natural hydrogen from those settings. The natural generation type production would be very much analogous to a geothermal type system, where you have fluids again moving through the subsurface and you drill down and you start producing them. And so again, I think that it would be minimal impact there. The stimulated, again, could have a lot of water consumption, could have a lot of bringing up of heavy metals and other contaminants that would need to be dealt with and so forth. And so that one I think has a lot more challenges to it.
Thank you.
Okay, all right. I think Elliot, you were next with your hand up. Go ahead.
Yeah, thank you. Thank you, Jeff. That was a great presentation. Very
Thanks.
interesting. My question is containment of hydrogen as it comes to the surface, and how that, if that's been developed, or if that's in a process of development as well. As we know, it's the smallest molecule, so.
Right. Yeah, exactly. And so we do have technology for handling, transporting, and storing hydrogen underground, right? We have existing underground hydrogen storage facilities that have been operating for 50 years or more, or so forth. So I guess I have to plead ignorance that I don't know how effective they are at mitigating leakage, although I think they're relatively effective.
Right.
But I think going forward, if this were to really take off and become widespread operation, that is a concern that we would want to make sure that the tolerances are going to have to be pretty tight in order to minimize that. Right now, the amount of footprint that we have for hydrogen infrastructure is relatively small compared to the oil and gas operations that we have across the planet. But I think that I know that we have the high grade steels, and we have the kind of fittings that they're able to minimize leakages. The other interesting thing is that microbes are very efficient at consuming hydrogen. And so if you have underground pipelines, for example, I think those, I don't worry too much about leakage there, because microbes will consume any hydrogen that's leaking up through the ground for the most part. And same with offshore. I've talked with my colleagues at DOE, and they're very interested in offshore resource development because of this fact that if you have hydrogen leaking out of the seafloor, it'll never make it to the atmosphere, I don't think, because they would get eaten in the water column as it's moving through.
I was thinking also on the economic side of it, the loss of production coming up whole, through the process of drilling. I know that there is generally in the oil and gas industry, there's always some type of leakage that has to be dealt with, but even more so with hydrogen.
Yeah, that's a fair point. And I don't know what their tolerances are. They do this underground storage, of course, routinely, and
Right.
There's definitely some loss there, right?
It's just a curiosity at this point. A lot more to learn, huh?
That's for sure. And I know that, hydrogen is an indirect greenhouse gas, as I'm sure you're aware. So there is definitely concern about, more leakage to the atmosphere. Although the one thing that I've discovered recently is that the atmospheric chemists really don't know much about how much natural hydrogen is just leaking out of the ground and getting to the atmosphere. In all their models, they assume that the soils are net sinks and there's no hydrogen coming out of the ground. But I've been out measuring hydrogen in soil gases, and I can tell you that there's a lot of hydrogen actually in these soil gases, and that we have active vents, places, these eternal flames, and you see in Turkey and stuff, those have very high hydrogen concentrations. And so there's a lot of hydrogen that's leaking out of the ground naturally. And in fact, if we go out and start producing it from the subsurface, we might actually reduce the amount that's naturally leaking out of the ground because we're capturing it and putting it into pipelines before it has a chance to leak out at the surface. So,
Interesting.
Yeah,
Thank you.
Jeff, the way that Vyacheslav Zgonek put it, he said the Earth is leaving a wake of hydrogen like a comet. Do you agree with that? Yeah.
No, that's true. Yeah, it's
and-
actually monatomic. There's just hydrogen atoms that are streaming off of the Earth's atmosphere. We're constantly leaking it, and it's a comet tail that goes out past the Earth's moon, in fact, out into space. Yeah.
Yeah, and I think, I think it's fair to say that all those analysis, like you said, assume that the Earth is not outgassing hydrogen, and so we're adding a little bit to that. But if that's not at all the case, we may be adding 0.001% to something already there. So, more study is needed, obviously.
Yes, absolutely.
All right, Jack Steinhauser has his hand up.
Yeah. Hi, Jeff. Thank you very much for your presentation. It was quite informative. I come from an oil exploration background, and in our business, we always talk about petroleum systems having source, migration, trap, and seal. So my questions today are primarily on what happens during the migration process, because you talk about consumption in your diagram. And the question is, does that apply at depth? Are there microbes at depth or something else that's causing consumption?
Yeah. It's a great question. And there absolutely are microbes. There's actually, that's a lot of what we know about hydrogen in the subsurface comes from the microbiologists. There's been, over the last few decades, a growing recognition that there's a major biosphere that exists in the deep subsurface that subsists primarily off of hydrogen.
Wow.
You go to places like Yellowstone, and there's a lot of hydrothermally generated hydrogen, and then there's these whole microbial consortia that are living around these places in hot springs. So from a resource perspective, though, what we're looking at is we want to find the places where the microbes aren't consuming it, right? And so they tend to be happiest around 40 or 50 degrees C. And as you get to higher temperatures, they get less and less efficient at consuming hydrogen. And certainly once you get much above 100 degrees C, they really can't persist at all. And so there's a thinking that there may be a sort of a sweet spot. The other problem is that at much higher temperatures, when you get above 200 degrees C, you can get abiotic reactions. CO2 and hydrogen can combine to form methane through a Sabatier type of reaction. And so it's thought that there might be this sort of sweet spot between 100 and 200 degrees C where you could preserve the most hydrogen. That said, that discovery in Mali, it was discovered accidentally because they were drilling shallow for water. The shallowest reservoir is only a couple hundred meters below the surface, and the temperatures are quite low, and yet it's over 98% hydrogen. And so when I talk to the microbiologists, they say, well, probably at some point when you get a high enough concentration of hydrogen, it becomes toxic to the microbes. They can't survive in an environment that's pure hydrogen. They need other nutrients, and they need other elements in the environment. And also there's a paper that just came out a couple of weeks ago in Science about another discovery in Albania in a chromite mine, where in a fault zone, they found a pretty substantial reservoir of high purity. I think it's 84% hydrogen. And again, it's quite shallow. It's less than a kilometer deep. The the lower temperature end is around 40 degrees C, which is ideal for these microbes. And so again, seems like there are environments that microbes need certain nutrients, they need water, they need other things to consume hydrogen. And so if those are absent, then you can preserve these accumulations.
Okay. So the second part, of course, is the trap. And
Right.
in gas exploration, we know that there'll be a distribution of field sizes based on the size of the traps. So you've got your giant, your supergiant, your large, medium, and small. Do you expect
Right.
something similar for hydrogen, that there will be this kind of statistical distribution of field sizes similar to what we see in oil and gas?
Yeah, that's a really good question. And, I mean, I'll go out on a limb here and speculate. I mean, because we just don't have enough data to really know. But my gut feeling is that, yeah, we would expect some kind of statistical distribution like that. And the key difference, though, being that I expect that not only will we be looking for these resources in sedimentary type of reservoir settings, but also in hard rocks. And in fact, this discovery in Albania was in ultramafic peridotite type of rock, that not your traditional type of reservoir. It's a fractured reservoir in crystalline rocks. And in fact, when I started first looking into geologic hydrogen, my background is in oil and gas and in gas geochemistry. And so, my thought was, well, we're not going to get the reservoir where the places that you're generating this hydrogen is not so much in the sedimentary basins. It's going to be in these more hard rock settings. And so you're just not going to get the reservoir rocks. And then I started looking into oil and gas reservoirs in crystalline, in hard rock settings. And it turns out, in fact, there's a lot more of them than I realized, and that, we kind of ignore them, but in fact, they are out there. And they're all been discovered, to my knowledge, they've all been discovered accidentally. They were poking around, they happened to find big gas fields, and some of them are actually world-class reservoirs in volcanic rocks, for example. And so I think that the same could very well hold for hydrogen. We just haven't looked for, hydrogen gas in volcanic rocks ever.
So when you say world-class, do you mean the size of it or the porosity and permeability of it?
Both. Yeah. I don't know if there's a gas field in Indonesia, and it's like, I want to say 30% porosity or something like that, and 10 in the Darcy permeabilities, and it's multiple TCF of gas, all hosted in a volcanic rock.
Yeah, so that's very interesting. Okay, last question has to do with seal. So it seems like if hydrogen has such a propensity to penetrate through anything, so what kind of seal do you need? Because in oil and gas, we measure the effectiveness of the seal, and at a certain point, the oil or gas is not going to move. But hydrogen is going to do that. So talk about that.
Yeah. That's the other one that, again, when I first started looking at it, I was like, well, okay, you're not going to get reservoirs, you're not going to get good seals that are going to hold this in, right? And then I've done a lot more reading on this, and it turns out that the diffusivity of hydrogen is actually very comparable to that of helium. And if you look at the kinetic diameter of the diatomic hydrogen molecule, it's actually a little bit smaller than a monatomic helium atom. And so there are known helium accumulations that have been trapped for over 100 million years.
Yeah.
And so I think that the notion that hydrogen's so diffusive you could never trap it for any length of time, that I think has been overblown. And so I think that you could still get, it is certainly more diffusive than methane. You can get that, you can look at lab experiments and it does diffuse more readily than that. But it's not so diffusive that you could just never trap it at all. And so I do think, a good evaporite and even a shale can be an effective seal, more or less. The other key is that the generation rate is so much faster that you don't necessarily have to preserve it for as long. You could generate it over thousands of years, and that would be a lot, whereas in 1,000 years you're not generating very much oil and gas.
Okay, so I'm going to make a prediction that somebody's going to find a giant hydrogen field based on what you just said. Reasonable?
I think it is reasonable. I absolutely do. Yeah.
All right, thank you very much.
Yeah, you bet. Brian, you're on mute. Yeah.
Yep, I just got a notice on it. Sorry about that. So, Ray Pilcher out in Grand Junction has a question. Go ahead, Ray.
Hey, Brian, and thanks, Jeff. I have a couple of questions. Well, and a comment. I was in Albania last December, and I'm going back in April. That chromite mine that the hydrogen was found in was also found accidentally, unfortunately.
Mhm.
Killed a couple of people and burned
Yeah.
some up. And so they're still working out exactly what it is, but there's a number of that's a province up there of chromite. So it may be much bigger than anybody recognizes at this point. So there may already be one of these giant fields.
Right.
But the question I have two quick questions. One is when you talked about the amount of hydrogen in the crust, and then we talked about all these other potential systems that can generate hydrogen. It seems like to me the system's not closed. I mean, it's, of course, we only have so much hydrogen on the planet, but you're also liberating it at different rates. And so I'm just not, and recombining. So I'm not really sure how you get that number, I guess, is basically where I'm headed is.
Yeah. So, so the number that we came up with was really based on what might be trapped, just held in traps and accumulations, today, and it's based on what we see coming out. We have some estimates of what we're measuring at the surface from, say, volcanoes and hydrothermal systems and so forth, and then there are estimates of what the generation rate is through radiolysis and through iron oxidation, water reduction reactions, and what the concentration or the how much iron is in the subsurface. And so those are all published numbers. And so we ran a Monte Carlo on all of those. And then on the trapping part, we use petroleum system. There's really nothing about how much hydrogen might get held up into traps. So we use petroleum system as an analog for what percentage might get caught up in traps. And we used a lower end of that, not with the thought that it's a gas, and so it maybe doesn't get trapped as efficiently as oil, and then used helium essentially as an analog for what the residence time might be for accumulations, and so I think one of the keys is that the output that you saw was huge, right? There was a wide range, anywhere, it might only be thousands. If all the low ends come in at the low end of what we're thinking, then it might only be thousands of megatons. And and I think that's unlikely, but it's within what we're thinking, But on the other hand, it might be in the billions of megatons, which would be enormous. And the other thing that we didn't really account for that Brian has talked about, Vyacheslav Zagonek, and I don't know if you've seen any of his work, but he and many of his Ukrainian and Russian colleagues are very much of the belief that there's a lot of primordial hydrogen trapped in the earth, and we didn't really put much emphasis on that. But if that really is true, then it really could be a very enormous resource, and could be very much kind of like what you're saying about an open system, where they think that the Earth's core actually is made up of nickel iron hydrides, and that there's all this hydrogen there, and it's sublimating and leaking out. And so we have this huge source of hydrogen, and it's migrating up through the mantle, and it's seeping up through these deep faults into the crust. And I'm open-minded about that. We just don't know the answer to that. But if that's true, then there could be really enormous amounts of hydrogen coming up.
The other thing that I wanted to mention, and Brian, if this is too long and we're getting too far into geology, then you can mute us. But
go a couple more minutes. Go a couple more minutes.
Oh, okay. Well, this one's quick, actually. You probably also know, Jeff, that one of the discoveries in France now is in the Lorraine coal field.
Right.
And when we've done a lot of desorption and adsorption in related to coal bed methane and coal mine methane, et cetera, one of the things that we had to deal with was that we used to measure all the total gas that would come out of the canisters as we were measuring, but we found out through some research that had been published is that some of that at the end is actually hydrogen, and that the belief is that there are microbes that are actually generating hydrogen in that coal seam. But it also seems like to me that there's a possibility, particularly in France and maybe some of the other coal mines, is that actually the hydrogen is not just being generated, but is also migrating from the deeper part of the basins, et cetera. And I just wonder, has there been enough work done yet on the isotopes to determine if these are all of the gas associated, all the methane, or sorry, the hydrogen associated with coal, is it all generated by bacteria recently, or is some of this actually deeper and migrating up through these systems?
Yeah, I think that the answer is that we haven't done enough research on that to answer that question. But also, I think it's a difficult one to answer because from what I've seen, the hydrogen isotopes on molecular hydrogen are not that diagnostic. It's difficult to get a clear source signal out of that. But also, you mentioned that Lorraine discovery, and from what I've seen out of that, that seems like a lot more hype than real discovery yet at this point, because we very commonly find hydrogen associated with coal gases, and so they were actually looking for coal bed methane and then found hydrogen associated with the coal bed methane. And then the giant discovery that they claim is based on extrapolations of those concentrations down to greater depths. But I don't think there's any real basis for that extrapolation. They need to go out and prove that. And so I've been told that they are planning to drill deeper and will test that idea. But yeah, I'll be convinced when I see some data from greater depths in that site.
Yeah. Okay. All right. Well, thank you very much. I really appreciate it.
Sure, my pleasure.
Thanks for your questions, Ray. Well, I think maybe we will kind of wrap this up now. I will say, Jeff, one of the things you said when we did the podcast was, please don't give out my email. I'm too busy. And so to everybody on the call here, try not to bug Jeff if you don't have to. I think one of the good things we can all wait for is that USGS website that's going to come up, that's going to have some good information. And I'm certainly going to continue to track this and provide information. Either maybe we'll have you back again, Jeff, if something warrants it on the meeting here, or we'll cover it in the newsletter or whatever. So I guess I'll say that. But let's conclude with one question, and that is, what do you think the possibility or probability is of us finding natural hydrogen here in Colorado? Do you think the geology could possibly warrant it?
Yeah, I think so. The mapping work that we're doing now is on the national scale, and so the preliminary results that we're seeing out of that Colorado doesn't really show up as being a really that perspective compared to other parts of the country. But I do think that when we get into a more of a exploration scale and really looking at smaller geologic features and stuff, I do think that Colorado absolutely has the potential. So the whole Rocky Mountains will certainly have some potential. Yeah.
All right, great. Well, I'm going to call us on this now, just so we can move on to some of the other things that we had planned. But Jeff, again, thank you so much for your time. Really appreciate that, and encourage everybody to go back to the podcast. There's information there that we didn't cover here, so check that out. That was the last one we did. I think that came out last Friday or maybe the week before. So encourage everybody to check that out. All right, Jeff, thank you again. All right. So Jane has been patiently waiting. Jane, are you still out there?
I am here.
All right. Well, Jane is with Elektrikgreen, the founder and chief executive officer. You can see that there. And gosh, we did a podcast years ago, I think, with Elektrikgreen, and Elektrikgreen is continuing to develop, I don't know if you want to call it products, but it's certainly at least new services and things. So I thought it'd be a good idea, Jane, for you to come back on the meeting here and just tell us all what you're doing. And I'm going to stop sharing and let you share.
All right, that sounds great. Let's see here if I can get things started.
Here we go.
I started my video but I think I'm gonna stop it before I give the presentation. But I just wanted to chime in and announce, who I am, obviously. Brian, thank you for the introduction. And yep, I'm CEO and co-founder of Elektrikgreen. And I'm gonna shut off my video so that I don't have glitches with my somewhat flaky internet. So let me just do that and then I'll start my presentation here. Okay. Let's see if I gotta find my, gotta find my screen. There we go. Okay.
All
Are we
right, we've got it.
seeing-
Yeah, we've got it.
Okay, excellent. Excellent. So Elektrikgreen is providing clean energy storage and hydrogen production for electrification and green hydrogen fuel uses. And it's our goal to become the industry leader in clean energy storage and that green hydrogen production for businesses and homes in the US. And our solutions are patented. They're one of the first of their kind in the US market. Of course, it's a zero carbon, hydrogen-based dual purpose energy storage and fuel production system that can provide electricity for days to weeks and produce green hydrogen fuel on demand. So our core product has a dual purpose, and it's dependent on the need of the particular customer. If their need is just solely refueling or electrification or both, we have the solution for all of that. Our energy storage electrical supply system, which we call the Elektrikgreen Firefly, creates green hydrogen from renewables and converts it to electricity on demand. And of course, as all of you know, it's very safe. But of course, it is also scalable, it's recyclable, and it doesn't lose power over time like traditional batteries does. Our hydrogen fueling system that we call the H2Go can provide on-site production and fueling for fuel cell vehicles. And that H2Go refueling station is a unique modular configuration for direct hydrogen fueling stations. And we can scale them from fairly small output to high-end output production. So one of the nice things about our system is that we have multiple components. And so you can replace an individual component without taking the entire fueling system offline. Our hydrogen fueling output pressure supports both 350 bar or 500 PSI and 700 bar, which of course is 10,000 PSI, and is much safer than other fueling solutions because the hydrogen is stored at 35 bar. And our systems are scalable. Our product line was designed to meet a wide range of customer needs. So our systems can be provided in an all-inclusive trailer or as a delivered container unit. They are scalable and capable of energy storage in on-grid and off-grid remote locations. Our system creates and stores its own energy and hydrogen from the grid or through renewable energy sources. And when called upon, the system then uses that stored hydrogen to produce electricity and or hydrogen fuel. And our systems can produce anywhere from 5 to 20 kilowatts and are scalable to 500 kilowatts and beyond, and or produce 5 to 450 kilograms of hydrogen in 24 hours and are pretty much infinitely scalable. So here's a big picture of our larger scale fueling station. We have the electrolyzers, the storage tanks, the booster system with cooling for the 10-minute fast fueling times, and our smaller hydrogen boosters and fueling station pump, I guess you'd call it, looks something like this down at the bottom. And then we've integrated the components of all the system using a patented software process that ensures the system is efficient as it can be and has built-in safeguards. And users can track their hydrogen production and usage in an app that is accessible from anywhere. And pretty much I get all the time these questions of, well, what is the patent on the system? Is it on the components or a control system? What is it on? And it's really what automates the system, and it automates it so that it thinks more like a human. And that's really what our patent is on, is the integration of all these components and how they work together. So it's smart, it learns, it predicts and responds, unlike any other hydrogen energy system that we've seen on the market today. And then we have several other patents in process right now, one of them being our hydrogen booster, which does manage to take the stored hydrogen and boost it up to the up to the 10,000 PSI. So I threw this in. It's a whopper of reading material, but yeah, I knew you guys would all probably want to know some of these answers. And so I just thought, okay, I'll put in this long-winded slide and you guys can digest it for a few minutes. There's really not much. I mean, overall, it's we have two different fueling systems. One that can fuel more like you would charge a electric battery operated vehicle. And so you basically could have this at home. You could plug in your fuel cell powered electric vehicle and get it to a fill point. You could use either the 700 bar nozzle or a 350 bar nozzle. And if you were completely empty and you needed 5 kilograms, you could do it at 700 bar in a little over 2 hours. So that's equivalent. Actually, it's much better than charging an electric vehicle that's battery operated. So that's a nice option for small fleets that maybe park their cars at night, or even the homeowner, as I mentioned before. And then we have our fast fill H2Go fueling system that will fuel a vehicle at 5 kilograms in 10 minutes, a little under 10 minutes technically. But so, all right, we can come back to this if you want to. So here's the advantages of our fast filling H2Go system. You know, and one of the things that we really like about it is that it is a lot safer. You can have it all entirely contained in a 10-foot container unit, and it's a much lower cost than what's currently out on the market. And then the advantages to our trailer system, which we have our Firefly, our energy electrical system in, as well as we have our smaller version of our H2Go in. Of course, you know, it's all in one unit, so that makes it really simple. You can move it around if you want to. It's just very, very simple to have. It's very plug and play, and you don't have a lot of fuss and hassle with it. So, and then this just generally goes over how we can scale up our storage and how we contain the hydrogen in general. Everything, of course, is 100% recyclable should you need to do that, but they are certified for 20 years. And some of you might know the company who makes these tanks for us. Of course, it's Steelhead. Whoops, sorry. And Steelhead has been a fabulous partner with us, and they work very efficiently. And they've built out this really nice containerized tank storage system, which will pair nicely with our fast fueling system. So our pricing ranges, starting as little as 80,000, going up to over $1 million. And just to talk about pricing, I'm sure we're all aware that, of course, there's a 30% incentive available, tax incentive available. That's for energy storage. There's the $3 per kilogram available for green hydrogen, which we do highly promote. Of course, some people must and do just plug our system into the grid. And that's, that's just another option. Obviously, that is not green hydrogen. So we just wanted to point that out. We do encourage people to either buy RECs, renewable RECs, or have solar, wind, or hydropower to power our systems. So some of our applications are, pretty broad. Technically, we can provide green hydrogen long duration energy storage. So that can apply to so many different things, as well as, of course, our fueling. And so we have residential, commercial applications, everything from fueling buses, cars, forklifts, to backup energy for buildings such as grocery stores or telecommunication systems, microgrids. And then, of course, we have industrial applications, some of our largest systems for providing hydrogen for metal refining and ammonia, such things like that. And that's all I have for you today. So if you have any questions, let me know. I'll just stop sharing here.
Well, thank you, Jane. Yeah, let's open the floor to questions. If anybody's got questions, comments, or other things. Oh, I see Frank Zamataro got his hand up. Go ahead, Frank.
Oh, here we go.
Pretty awesome. It syncs up nicely with what we're working on as far as small hydro for water operators to potentially power hydrogen fleets. So it's very nice. I like the packaging. Where are you commercially in terms of building systems, deploying them? So give me some sense of the maturity of the configuration, the integrated system, and where you'll be potentially doing some of these in the not too distant future.
Yeah, so we are currently building out several systems, and I guess I'd like to say that we're basically in beta and fringing on commercialization. That's more or less where we are. We have some systems already out there. We've had systems that have been in operation since 2019, 2020. And we're looking towards really getting some of our fueling stations out there right now, as well as we have a customer in California who is looking to go into our telecommunications market. So.
One last question. Thank you for that. One last question. What form of electrolyzing are you using within your system?
We are using a AEM electrolyzer.
Thank you.
Mhm.
Okay, I don't see any other hands up. Have we got other questions?
Yeah, this is Howard Gerwin. I can't find the button to raise my hand. So,
Okay.
so two quick questions. Why, I guess, if you're going to go live on camera, I will show my face as well. In my messy office. How did you pick the 30 bar storage? Excuse me. How did you end up with 30 bar as a storage level? I assume you're just storing as compressed gas. How do you end up there?
So it's 35 bar, which is 500 PSI. And how we got there is that our AEM electrolyzer outputs at that pressure. So we don't have to do any compression.
Until you need it compressed. Okay.
And yeah, until and if we need it compressed. So for instance, for refueling or fueling vehicles and forklifts and things like that, drones, etc., we do use the compression.
Okay.
Yeah. But for like our energy storage system, we don't need any compression at all.
Okay. Have you looked at any of the adsorption or hydrides or any of the other storage media sort of as a part of your, okay.
Yeah,
and I'm glad that stuff's not ready for prime time yet.
Yeah, I mean that's definitely the case. And you know, we have looked at a lot of it, and our CTO is not prepared to go down that path. This is something that we can look to in the future, however.
Okay. I had another question, but it's vanished, so thank you.
You're welcome.
Maybe it'll come back, Howard. Anybody else, questions or comments? I think you can all see why I wanted Jane to come on the meeting here, because you guys have a lot going on. And I will add that, and Jane, correct me if this is wrong, but you've been using a hydrogen energy storage system at your house, which is off grid, for some time. Is that right?
That is correct. We have been using it since, gosh, well, we incorporated in 2015. I think we built out our first prototype in 2018. I think that's right.
Mhm.
And so, yeah, we've been doing it for a while, and kind of in stealth mode, I guess. But we are right there at the cusp of really having a lot of customers and a lot of things happening. So it's very exciting.
Yeah. Well, the nice thing is, for home energy storage, you need so much less energy than we need in a car, and so it's a little bit easier in that case. And I know that system started pretty small with the adapter electrolyzers. I think they're 1 kilogram a day, if I remember right. And you just basically put those in parallel to get the hydrogen you need. So nice
Yeah.
system. Yeah.
Yeah. Pretty much through the process, Brian, over the last couple of years, we've gone away. So we are kind of a combination of system integrators and manufacturers. We ended up not being satisfied with a number of things that were off the shelf, and so we've ended up developing several of our own proprietary systems. One of them being a fuel cell, one of them being our fueling booster system, our H2Go. And then we went from our, first iteration and our lower cost H2Go, which does the 5 kilograms in under 2 hours, to our now 10-minute fueling H2Go, which has been, quite a bit of a leap for us to figure out and to get that accomplished. So we're very excited about that, and we hope that, a lot of you are excited about it.
Well, I am, I'll say that. So you guys have really been busy there up on the mountain there in Lyons. Definitely off grid up there.
Yes, we are.
All right. Well, I don't see any other hands up, and I did have a couple of other things to cover. So, Jane, maybe we'll leave it at that. And I just encourage people to get in touch with you. And we ought to do another podcast. There's a lot has changed since the last time. So
yeah,
consider
that'd be
that.
great. Thanks, Brian. Appreciate it.
All right, Jane. Well, thank you. Let's see. I need to share my screen here again. And it's funny. And I've said this before. Every month, I get worried about not having enough material, and definitely got more material than needed today. But I do want to touch on something because it is timely, and that is the Colorado Energy Office. You can see the logo there has put out a request for information, and as you can see here, it says that this is kind of intended for market research purposes. And they're going to use this information to guide a study, which is called the Colorado Hydrogen Infrastructure Study. And the RFI it's a long URL. So of course I had to do a little shortcut here. So it's tinyurl.com/H2RFI, due March 1st. But I'm busy working on a response to this, and I encourage any of you out there to maybe consider doing that as well. Okay, come on. How come I can't? There we go. So the study itself will be conducted in 2024, and the intent of that is, you can read it, is to inform the design, development, and implementation of a fueling infrastructure grant, which is known as SHINE, which is the Sustainable Hydrogen Investments for a New Economy. And this will help with the strategic build out of hydrogen fueling stations, and those are really intended to support medium and heavy duty vehicles. And I think that makes a lot of sense. I know Maria Eisenman was on a little bit earlier. Is there anything you want to add to that, Maria? I don't want to put you on the spot.
No, fine. Yeah, this is out till March 1st. And even if you just want to look at it, or maybe you only have one item you could contribute to, would still like to hear from you. And especially if, this study that we're going to do is going to inform the design of this funding program for hydrogen fueling stations. And we're just really looking for, are we forgetting it? Or is there something we don't know about? Or is there certain things that we should definitely take into consideration? So even if you might only have a little bit to contribute, that's fine. We'd like to have you fill it out still.
All right, good. Yeah, thanks, Maria. And there's obviously not a lot of time here, it's a couple of weeks, but if you just want to make one comment, that's all you need. So the RFI itself has, I've just pulled out a few examples of some of the things that they're asking, but technical, they're asking for some input on gaseous versus liquid hydrogen. And I think I would even add to that ammonia or LOHC, liquid organic hydrogen compounds, for that as well. How about where are we getting the supply, and what kind of transport do we want to look at for these fuel stations? Safety, liability, issues with the utilities if we're going to be using electrolyzers. Obviously, grid connection is going to be needed. And then are there anything like permitting and zoning, things that the state could help with? And then on the financial side, they're asking for a little bit of information about how the grant incentive should be structured and the amounts and the timeline. So that's not a comprehensive list, but it's just to give you a sampling of some of the things that are being asked there. So here is the proposal that I'm putting together. This is basically the table of contents on this. And I wanted to talk, and I'm going to show you this if we have time here. I've got to talk fast, but about the pricing issues around hydrogen, sourcing, and then I go into quite an analysis on the cost of hydrogen. And I'm getting help from Starfire, that company that's here in town on the ammonia. Also getting help from Gen H2, who's another stakeholder of CHN as far as liquid hydrogen and the cost to transport that. And then I've got some messages into some folks I know on the LOHC. I don't know if I'm going to get that in time, but these are some of the things that I'm trying to cover fairly comprehensively here. So I'm running a little low on time, but let me pull up everything here and show you that I believe that hydrogen has got to compete with petroleum. And basically what that means is that if you're driving a gasoline vehicle and you get the same type of vehicle that is hydrogen fuel cell, you want to have the same cost per mile with that hydrogen vehicle that you had with gasoline. And so to kind of compute that, we want to look at this, what's called the EER. I'm having trouble getting my slides. There we go. Which is called the energy economy ratio. And so what that means is that if you were to take a gasoline car and a very similar size and weight car that runs on hydrogen, you can expect the hydrogen car to get 2.5 times as many miles as the gasoline vehicle did. And for light and medium duty diesel, it's about 1.9. But here's one that is really kind of throwing a lot of us, and that is for the Class 8 heavy duty diesel vehicles. Their EER is only about 1.1. And that's expected to improve a bit, maybe to 1.3. But that makes it really difficult to come up with a source of hydrogen that can compete with diesel for those big vehicles. And so I'm going to, well, I wanted to skip this, but I see now that I can't. I think the sources of clean hydrogen, we just talked to one, which was the natural hydrogen wells, but I really think, and this is something I've talked to many times on this meeting, is the underground hydrogen generation, which is basically taking old oil wells and generating hydrogen underground, which is clean because you never bring methane, you never bring carbon out of those wells. But the natural hydrogen wells, I think, in the underground hydrogen generation are going to be cost competitive enough to where even if you transport that hydrogen, it'll be cheaper than electrolysis. And I'm going to show you that in a minute. I don't have time. I'm not going to go through these block diagrams of how we move hydrogen as ammonia or liquid, or LOHC for that matter. I'm going to cut to the chase here. So this is very, very preliminary. I made up some numbers it was my best guess at what these different scenarios would cost for 50-mile delivery and the equipment to change gaseous hydrogen to either a liquid or ammonia or LOHC, put it on a truck, transport it, and then crack it back to hydrogen at the fuel station. And I'm coming up with preliminary numbers here of maybe 549, 550 for LOHC liquid, maybe 610 a kilogram, ammonia 689. And again, I was guessing at the CapEx, I was guessing at the OpEx. I'll have better numbers for the actual submission of this. On-site electrolysis, we know that very well. It's probably in the neighborhood of 816. And by the way, this is based on a certain amount of return on investment of that capital equipment. So that's this column here. All right, so what does this mean? Well, if we go back to the table I just showed you about the energy efficiency ratio, we've got these target sales prices for the hydrogen. We've got cost. All right, so where does that kind of leave us? Well, electrolysis is really only competitive for the light duty and medium duty gasoline vehicles. Ammonia, liquid H2, and LOHC, I think, can be competitive for all the light and medium duty vehicles. But I'll be darned if I can find a way to get to a competitive price for the heavy duty. And I know, like I say here, hydrogen for heavy duty transportation is a popular idea, but I don't know how we get, and by the way, this is assuming that the hydrogen at the well is 30 cents, which is the number that's per kilogram that Proton Technologies has been bandying about somewhere between 25 and 30 cents a kilogram at the well. Transport just eats your lunch. And I don't know of any way around that. And you can see the on-site electrolysis doesn't get us there. So this is where I am right now. Now, again, I'm coming up with better numbers here. Jen and Joe Beach are giving me some numbers for ammonia. I'll crank that in here. I'm hoping to get the liquid numbers as well. Don't know if I'll have the LOHC, but this is one of the things, and I see Maria's looking intently here. This is a place I think this study that the state could put out is there a way to transform that gaseous hydrogen at some source into a form that can be trucked, and can we get it to a station at a price that really could compete with gasoline and diesel? Now, I know there are no tax breaks, incentives, grants, or other things in here, which will certainly help early days. but eventually those go away, right? So somehow we've got to get to a cheaper way of moving hydrogen around. So um, I guess I'm kind of just throwing out a question here more than anything else, but this is where I'm trying to go with this study, which I hope will help the state to kind of target some things to look at in a real detailed study. So
Yeah, yeah, thanks, Brian. And and that is the thing is we're gonna use this RFI is not to help us answer the question because what's coming out of this RFI is the design of a study. So we're looking for study questions or how should we scope this? So this is helpful in the context that you're saying, hey, you should look at this because my preliminary shows this. So one of your questions should be, how do you do? So that's just to, and I'm glad you were couching it in that respect, is that this is to inform the design of a study, not the program itself yet.
exactly, and that's really my point. I didn't say it that way. Is
Oh, no, I think you did, actually.
here are the questions. Because I've been looking at this for what 4.5 years now, and scratching my head over some of this. And by the way, like I say, this is all predicated on 30-cent hydrogen coming out of the ground somewhere. And that's possible, it's feasible, but in order to do that, you've got to spend millions to come up with that well. And so, maybe that's where some of the grant money needs to go, is to say, hey, we're going to develop a well, I guess, put it that way. And, Colorado's got 20,000 abandoned oil wells that could be used for this. So, I think there's some real opportunities here, but I don't see anybody else, talking to these kind of questions. And maybe it's, behind closed doors somewhere, but anyway, I've just got a couple of minutes left. So I think I'm just going to stop with that. I had a couple of other things, but really encourage folks to take a look at that RFI and send Maria, or send in to the RFI response any ideas you have. So let's see, Elliot, you've had your hand up quite a while. Is that just leftover, or did you have a new
No,
question?
no, I put it back up. First of all, I wanted to thank Maria and Matt and all the people over the state for initiating this study, this request for information, and we plan on making a full-fledged um, uh, presentation to you on that. So from our perspective as well, Ryan, this is good work. This really is. There's a lot of unknown questions as far as production of hydrogen. Obviously, our facilities are going to be delivered liquid hydrogen to our facilities, and then convert to gaseous or liquid depending upon the vehicle. And we'll talk more about that next month, which we're excited about. But I just wanted to say that you've done a really great job as far as how you've put all this together, and I'm really happy that Maria, that your office is really taking the initiative to really get this going, and appreciate it. So we're all in on this. So all together, I think. So any way we can help each other, that's great.
Yeah, absolutely. Well, and
Brian.
Elliot, your hydrogen is coming really from out of state because there are no sources here right now, right?
Right now, correct. Yeah,
Yeah.
we have long-term plans. I don't know, 3 to 5 years to developing our own hydrogen. We're working on some technology that'll greatly reduce the cost of production of green hydrogen. But that's another story, another day.
Yeah.
So, but that's the initiative, is to drive these costs down. I was looking at an article about $36 a kilogram for hydrogen at the pump for cars out in California right now, and I'm going, that's just totally insane. So,
Well,
just
that's gonna kill that. But I think
well,
one of the important things here is that we absolutely need a source of really cheap hydrogen. I think the tendency is to say, well, how do we get fuel stations going? Well, yeah, we can do that with the electrolysis, and that'll be fine for light duty vehicles, but light and medium. But we maybe need to really be thinking about, let's find an old abandoned oil well somewhere. Let's develop this into a hydrogen producer. Um, maybe. So at any rate, well, I am a stickler for trying to end these meetings on time. Maybe, I don't know, is anybody else who we could maybe do one more question if you have it, but we are on the hour. I guess that wasn't much of a sales pitch for getting people to comment, but
Thank you. It was awesome, Brian.
all
Thank you.
right. Well, thank you everybody for participating, and let's keep the faith, I guess, put it that way. So thank you, and I think we'll adjourn.
Thank you.
Yeah,
All right, thanks.
Thanks.
Thanks, Brian. Much
All right.
appreciated.
You bet. Thanks again, Jane. Bye-bye.
Brian?
Yeah, I'm still here.
Yeah, give me a shout when you get a moment. Give me a call sometime when you can.
Oh, okay. Yeah, I'm about to run off here. My wife's
Not
got-
right now,
got
not
dinner
today,
ready.
but in the next couple of days.
Yeah, okay. Yeah, we'll
I
do.
want to fill you in on things that we got going on that will maybe help you and your questions.
Okay. Okay, good deal. All right, Elliot.
Bye-bye.
Okay. Thanks. Bye, everybody.